Okay, today we're going to talk about equations of planes. Now, with lines, in the previous lecture, I want to remind you of something. To write the equation of a line, we had to have a point, and that told us the location of the line. And then we also needed a vector, and that told us the direction of the line. And with those two things, then we could draw a line. Okay? Now, for a plane, what does a plane look like? Plane looks like this. It's like a sheet of paper. Okay? Now, what two things do we need to describe the plane? With a line, we needed a location and a direction. Okay? So that meant a point for the location and a direction vector for the direction. Okay, for a plane, we also need to know its location and the direction that it's facing. Okay, so to pin down the location, we need a point that pins down the location of the plane in space. Okay, then for the direction, that gets a little bit trickier, and I actually said the important word just a second ago, but let me do this for you first, okay? If I said to you, look at that line for a second. If I said to you, what direction is the line going? Then that red vector demonstrates that perfectly, right? And the red vector could be pointing the other direction, 180 degrees opposite. That would be okay too, right? And that's called a direction vector. Okay, now, if I ask you what direction is the plane going, that would not be a sensical question, really, because here's the problem. The plane goes in all sorts of directions, doesn't it? 360 degrees around, doesn't it? So what do I mean when I say, what direction is the plane going? That doesn't quite make sense. So what we say instead is we say, what direction is the plane facing? Because then there's only two possibilities for that, just like with the direction vector of a line. It could point one direction or 180 degrees opposite. So for a plane, we want a point to nail down the location, and then we want a direction to nail down the direction that the plane is facing. Okay, and that could go that direction there, or technically it could have gone the other way like that. Okay, now let me see if I can adjust that angle a little bit. No, I don't think I'm going to be able to. Okay, so the thing about that red vector over there on the plane, you see, that is perpendicular to the plane, or I should use the word orthogonal to the plane. Okay, now when we're doing lines, okay, this is a point, obviously, right? And this vector is called the direction vector. Okay, remember we use D for that. And with those two things, you know exactly what the line looks like, and we even talked about in the previous lecture how to write the equation of the line with those two things. Okay, now for a plane, we have a point, and then we have the vector. Now that's not called a direction vector because it doesn't go in the direction of the plane. It goes the direction that the plane is facing, and that is called the normal vector. And we use n for that. So that's what you need in order to describe a plane. You need a point and a normal vector. Okay, now let's talk about how would you get an equation for that plane. So let's say that our point that's given to us, let's just call that x naught, y naught, z naught. Okay, let's call the normal vector ABC. I want an equation that describes the plane. In other words, I want an equation that describes every point on the plane. All right. Suppose there's a point right here. Let's call it Q. And that point could be anywhere on the plane. So I'm just going to write x, y, z. What's the one thing that I know? Well, I know this. I know the vector from P to Q is orthogonal to n. Because the vector from P to Q lies in the plane, and n is orthogonal to the plane. Okay, so we know that the vector from P to Q is orthogonal to the vector n. Okay, that means, if you remember about dot product, that means that the dot product of the vector PQ with the vector n must be 0. Okay, what does the vector PQ look like? It's the vector from this point to this point. So it looks like this: x minus x naught, y minus y naught, z minus z naught. That's vector PQ. Okay, we know that the dot product of that with vector n must equal 0. What is the dot product? That dot product is a times x minus x naught plus b times y minus y naught plus c times z minus z naught must equal 0. All right, let's simplify some more. That means that ax minus ax naught plus by minus by naught plus cz minus cz naught must equal 0, which means that ax plus by plus cz must equal ax naught plus by naught plus cz naught. Now, a quick thing to point out here, okay? These three things are variables because they're the coordinates of Q, and Q could be anywhere on the plane. I'm trying to find a equation that would tell me what does it mean for Q to be on the plane. Okay? So x, y, and z are variables. A, b, and c are numbers, though, that are given to us. And x naught, y naught, z naught are numbers that are given to us. So that means on the left-hand side of the equation we have three variables with a number in front of them, and it's added together. But on the right side, this whole thing is a number that you could multiply and add out and find out that number. Okay? Now, our textbook, along with every other textbook I've ever used, calls that number D. Don't get confused. It's not a vector D like the direction vector of a line. Okay, they just call it D because we already have A, B, and C. And so they use D as the next variable. Okay, so we have AX plus BY plus CZ equals D, which is a number. That is what equations of planes look like. So for instance, here's the equation of a plane. If I said 5x plus 7y minus 3z equals 12, that's the equation of a plane. Okay? And I can see which direction the plane faces immediately, because my normal vector is the vector 5, 7, negative 3. So I know that my plane is orthogonal to that vector. Okay? To find the location of the plane. So now that I have n, I know which direction the plane's facing. But to find the location of the plane is slightly harder. It comes from the right-hand side, from the number 12. Okay. You would have to ask yourself, five times what plus 7 times what minus 3 times what equals 12. And there's infinitely many solutions to that, and any solution would work. Okay? Like, for instance, one solution is to say 1, 1, 0. So that could be a point that I use to locate the plane in space. But there's lots of other points on the plane, and there's lots of other solutions to that equation, 5x naught plus 7y naught minus 3z naught equals 12. Okay? But I found one, which is 1, 1, 0, so that means I found one point on the plane. And so I could plot that point. I could plot this point. Whoops, I meant for that to be red. I could plot that point Then I could draw this vector from that point, and then I could draw the plane orthogonal to that vector. Okay? All right. So let's take a couple steps back here. So what I have highlighted there in green, that's called the general equation for a plane. Let's write that down. Okay, let's see. But this guy up here is just as good if you prefer. You can write the equation of a plane like this. And that's called the standard form. And this is called the vector form of the equation. All three of these equations accurately describe the points on the plane. Now the general form is the one that's most often used. Okay, let's move on. You probably heard in geometry class when you're in high school that 3 points determine a plane. Okay, so let's say I gave us a point, we'll call this one P, as the point 1, 1, 0. Okay, and a point 1, 2, negative 1. Let's call that one Q. And a point R, 0, 1, 2. So if 3 points determine a plane, then using those 3 points, I should be able to find the plane that contains those 3 points. So let's learn how to do that. So find an equation for the plane containing the 3 points (1, 1, 0) (1, 2, negative 1) and 0, 1, 2. Okay, let me ask you a question. What 2 things do you need in order to find the equation of a plane? You need a point, which will nail down the location of the plane in space, and you need a vector that tells you which direction the plane is facing. So, do we know any points on the plane? Of course, in fact, we know 3. We could pick any one of those 3. as the point that will nail down the location. Now we just need a vector that is pointing in the direction that shows us how the plane is facing. Okay? All right. We can do that by doing this. Let's look at that vector. We'll find that vector in a minute, and this one too. Oops. Let's find those two vectors, okay? And then let's calculate a vector that is orthogonal to both of those. Okay, so let me try to draw that in here. Okay. Okay, if that red vector is orthogonal to both blue vectors, and those two blue vectors are on the plane, then that means that red vector is our normal vector. So let me ask you a question. How do I find a vector that is orthogonal to two other vectors? Well, if you remember, we use the cross product. So let's do this. Let's write down these two blue vectors. Okay, so this one here, that goes from P to Q. So what vector would that be? That would be 0, 1, -1. This other vector goes from P to R. Whoops. So what would that vector be? It would be -1, 0, 2. So the red vector is, let me ask you a question. Is the red vector vector PQ cross vector PR, or is it vector PR cross vector PQ? Now let me say this. Either one would be fine. But I'm just asking you, the way I've drawn the picture, which one is it? You have to remember the right-hand rule. Okay? So think about that. The answer is, it is the way I've drawn it, using the right-hand rule, that would be PQ cross PR. PR cross PQ would be pointing in the other direction. Okay, but either one would work. You could use either one. I'm just asking you to see if you remember the right-hand rule. The one that I drew is PQ cross PR. Okay, so that is 0, 1, -1 cross with -1, 0, 2. And if you work out that cross product, which you should stop the video and work that out yourself right now and see what you get. It comes out to 2, 1, 1. So let's take that normal vector and let's just take the point P, although I could also use Q or R, it doesn't matter. You just need any point on the plane, but we'll just take P and let's write the equation of that plane. Okay, So how's that go? So remember, we have ax plus by plus cz equals d. Okay, there's a, there's b, and there's c. So let's put those in. Okay, there we go. 2x plus 1y plus 1z equals d. Okay, and what is d? Do you remember that? D is the dot product of your normal vector with the vector 1, 1, 0. And where's that coming from? 1, 1, 0. That's the vector that points to P. And what is that dot product? It's 3, right? So there's our equation for the plane. 2x plus 1y plus 1z equals 3. So that's how you can find the equation of a plane if you're given 3 points on the plane. Okay, how do you find the equation of a plane if you're given 2 lines on the plane? All right, let's say we have two lines that intersect each other. Okay, let's call these line 1 and line 2. So let's call this one line 1. We'll call this one line 2. Okay, what if you're given the equation of those two lines? So I'm going to write down the parametric equations. Remember that one? That's where you're given an equation for x, an equation for y, and an equation for z. Rather than one equation, you're given 3 equations. So suppose we're told x equals -5 plus 2s, y equals 1 plus s, and z equals -4 plus 2s. Suppose for line 2 we are told x equals 2 plus 3t, y equals 1 minus 2t, and z equals 1 plus t. Okay, now would those two lines be enough to determine the equation of a plane? Well, I have to say something about that. If they were parallel, then they would determine a plane, meaning if you're given two parallel lines, that's enough information to find the equation of one plane that the two lines have to lie on. Okay, but these aren't parallel because you can see their direction vectors. For line 1, the direction vector is 2, 1, 2. And for line 2, the direction vector is 3, -2, 1. And those aren't parallel. Okay? If the lines are intersecting, then they must lie in one plane. But if they're skew, then they don't lie in one plane. Okay, so what we have to do here is we have to see if these lines are parallel or intersecting, and I just showed you they're not parallel. So we need to show that they intersect each other. okay? And if they intersect each other, then that means they lie on one plane, and we want to find the equation of that plane. Okay, so the first step is to see if they intersect each other. Okay, so how do we do that? We talked about that in the last lecture. Okay, let's take any pair of equations, either the x equations, the y equations, or the z equations. Any one you want. I'll just take the x equations. Okay, we want to set them equal to each other. -5 plus 2s equals 2 plus 3t. Okay, what does that tell us? That tells us that 2s would have to equal 7 plus 3t. Okay, now let's take another pair of equations, either the y equations or the z equations. Either one's fine. I'm going to pick the z equations. Let's put them equal to each other. That would be -4 plus 2s must equal 1 plus t, which means 2s would have to equal 5 plus t. So 2s has to equal 7 plus 3t, and it also has to equal 5 plus t. That means 7 plus 3t must be the same as 5 plus t, which means 2t would have to equal -2, so t would have to be -1. Okay, that's useful. Now let's take the y equation, either one. Oh, sorry, not either one. We'll take them both. And we say 1 plus s has to equal 1 minus 2t. But since we know that t is -1, that means that 1 plus s must equal 3. I take that and put it right there, okay? Which means that s has to be 2. So those two lines cross each other when s equals 2 on this line, and when t equals -1 on this line. Oops, not 1, -1. So what point would that put you at? Well, plug a 2 into these guys, and what do we get? We get x would be -1, y would be 3, and z would be 0. If you take a t and plug it into these three equations, you'll get the same thing, won't you? You'll get -1, 3, 0. So that's where the two lines intersect. Because they intersect, I know that they lie on one plane. Let's find the equation of that plane. I already have a point. Let's just call that point P. Okay. I need to find a direction vector. Not a direction vector. I need to find a normal vector. Okay. I'm going to move the coordinates of that point over here to this side, okay? Okay, we need to find a normal vector. For the plane. Well, here's the key. I already know the direction vector for line L1. I wrote it down earlier. I can see it right here. 2, 1, 2. Okay. And I also know the direction vector for line 2. It's 3, -2, 1. So I can find this vector now by just doing the cross product of those other two. Okay. 3, -2, 1, cross with 2, 1, 2. And what do we get? We get -5, -4, 7. Okay, that's our normal vector for the plane. So now we can write down the equation of the plane. It'll be -5x minus 4y plus 7z equals, and for this number d, we just do the dot product of our normal vector with the vector for our point P. What would that dot product be? It would be 5 minus 12 plus 0, so it'll be -7. And there we have an equation for the plane. Okay, now let's talk about intersecting things. What if you have a plane and a line? That's not a line. What are the possibilities? One possibility is that plane, sorry, let me say this. The line might miss the plane entirely, right? It might be hovering over the plane, parallel to the plane. That's one possibility. Another possibility is the line might be lying on the plane. And then a third possibility is the line might be puncturing the plane. Really, it's intersecting, but I say puncturing because that sort of gives you a visual image. See, it might be poking right through the plane right there. Let me just redraw that line at more of an angle so that it looks for you guys more like it's intersecting. Okay, so I'm going to draw it like this. Maybe it's poking through the plane right there. And then I'm going to draw this dashed because that would be behind the plane. Okay. How can you find the intersection point? That's the question. I mean, assuming that you were told the equations of the line in the plane. So let's say this line is, I'm going to write down the vector equation for this line. What if that line is 3, negative 3, negative 1 plus t times negative 1, 2, 1. And what if the plane has the equation 2x plus y plus z equals 4? Now, I want to do two things here. Number one, let's prove that that line will puncture the plane, and then let's find the point where it punctures. Okay? How do we prove that the line intersects the plane? Okay, how do we show that that line punctures the plane? Here's what we do. You might not realize it, but if you think about it here, I know the normal vector to the plane. I know that it is 2, 1, 1, because those are the coefficients on the left side of the plane equation. Okay? I also know the direction vector for the line. It is negative 1, 2, 1, because it is in the equation of the line being multiplied times t. Okay? Now, if that line does not puncture the plane, then that means that the line would have to be parallel to the plane or on the plane, which means that the line would be orthogonal to the normal vector, because the normal vector is orthogonal to the plane. So let's test the normal vector dot, so that's the normal vector for the plane, dot with the direction vector for the line. Let's see what we get here. 2, 1, 1, dot. Dot product is always a lot easier to calculate than cross product, so I like the dot product. That's going to be negative 2 plus 2 plus 1, so it equals 1, which means it is not 0, which means that D is not orthogonal to N, which means that that line is not parallel to the plane and it is not on the plane, and therefore it must puncture the plane. So that's how I know the line punctures the plane. Okay? Now the only question is finding the point where it punctures the plane. I'll just label that point with a P, and we want to find P. And here's how you do that. Whenever you want to know where two equations cross each other, you just combine the two equations together. Okay, so let's talk in terms of the variables x, y, and z. For the plane, we have 2x plus y plus z equals 4. For the line, we were given the vector equation, which means I don't see the variables x, y, and z, but it's very, very simple for me to write down the parametric equations for the line. We would have x equals 3 minus t, y equals negative 3 plus 2t, and z equals negative 1 plus t. If you don't know why I'm doing that so fast, you might need to rewatch the lecture about lines. It's very easy. And what we'll do is we'll just take those and plug them into here. Okay? And that'll give us 2 times 3 minus t plus negative 3 plus 2t plus negative 1 plus t equals 4. Now you can probably finish on your own. It's easy now, right? You got 6 minus 2t minus 3 plus 2t minus 1 plus t equals 4, which is t plus 2 equals 4. So t equals 2. What point on the line would we be at when t equals 2? We would be at the point 1, 1, 1. Is that right? Yeah, that's the right answer. That's where the line crosses the plane. Okay. Next, what about 2 planes crossing each other? Okay, this is really hard for me to draw, so bear with me. I'm going to draw a blue plane and a green plane. Okay, and I'm going to draw a red line where those 2 planes are crossing. That's actually not too bad. Okay. Now, if I gave you an equation of those 2 planes, for this one here, I'm going to write x minus y minus 2 plus z minus 1 equals 0. So notice I didn't write the general equation, I wrote the standard equation. I prefer the general equation. So let's change that right now. That would be x. Let me write it down here. That would be x minus y plus z equals negative 1. You can check my arithmetic there. Okay, all right, for the green plane, we have negative 2 times x minus 2 plus y plus 1 plus z minus 3 equals 0. Let's put that into general form. That'll be negative 2x plus y plus z equals negative 2. You can check my arithmetic on that. Okay, so the question is, do the planes cross each other? If they do cross each other, what does the intersection look like? And find an equation for it. Okay, so when you take 2 planes, what are the possibilities for crossing or not crossing? Either the planes are the same, or they're parallel, or they intersect. If they do intersect, then their intersection is a line. Okay, so the first thing I want to do is figure out if they are intersecting or not. This is very similar to the last question. I know the normal plane for this, the normal vector for that plane, and I know the normal vector for this plane. Whoops, it's not a vector. I can see them in the equation. This one is 1, negative 1, 1. And this one is negative 2, 1, 1. That vector is orthogonal to that plane. This vector is orthogonal to that plane. Those two vectors are not parallel. You can see that by looking at their components, and therefore the planes are not parallel. So the planes must intersect, and their intersection is guaranteed that it is a line. Let's find the equation of the line. Okay, now, remember what I said. In order to find where two things intersect each other, you combine their equations, right? Let's take this equation right here. Let's solve that for z. We would get z equals negative x plus y minus 1. And let's take this equation and solve it for z. We would get z equals 2x plus, no, minus y minus 2. Now, if those two expressions are both equal to z, then they must equal each other. So we can write negative x plus y minus 1 must equal 2x minus y minus 2, because they're both equal to z. Okay, so that means, let's just move things around here. You can do it however you like. I'm going to write it this way. We would have 2y equals 3x minus 1, which means that y would equal half of 3x minus 1. Okay, now pick a value for x, any value you want. Okay. How about if we pick x equals 1? I just want to make sure you understand. I'm not solving for x. I'm picking a value for x. You could have picked 28 if you wanted. Okay. But if x equals 1, then what would y be? Y would be half of 3 times 1 minus 1, which is what? It's 1. So when x is 1, y would have to also be 1. Okay, and let's look up here. Z equals negative x plus y minus 1, so z would have to equal negative 1 plus 1 minus 1, which means z would be negative 1. What have I just found? I have found an x, a y, and a z, right? So what object is that? That's a point. I just found a point on this line. One, 1, negative 1. Okay. What else do I need besides a point in order to find the equation of a line? You also need a direction vector. Okay. Now we look at those two normal vectors for the two planes again. Remember that that blue line is lying on both planes. It's where the planes cross each other, so it's on both planes, which means that that blue line is orthogonal to both normal vectors. So what do you think I'm going to do? I'm going to do the cross product of the two normal vectors. 1, negative 1, 1, cross with negative 2, 1, 1. Work that out for yourself. You're going to get negative 2, negative 3, negative 1. So there is a direction vector for the line. And now I can write the equation for the line because I have a point and I have a direction vector. I can write L of t equals 1, 1, negative 1 plus t times negative 2, negative 3, negative 1. And there's an equation for the line. Okay. Okay, the last topic for this section is about distances. What if you have a plane and you have a point that's not on the plane? Let's call that Q. How can you find the distance from the point to the plane? Let's just call that distance h. Okay, so here's what you do. If you're given the equation of the plane, then that means in the equation of the plane, you can find a point and the normal vector. Sorry, I'll fix that p in a second. There we go. If you know the equation of a plane, then you can find a point and the normal vector. Okay? So this is very simple, okay? I'm going to draw the vector from P to Q. And that height, h, is equal to the length of the projection of vector PQ onto vector n. And you already know from previous lectures how to find that length. Okay, so h equals the magnitude of the projection of vector PQ onto vector n. And you've done this before. That magnitude is the absolute value of n dot PQ divided by the magnitude of n. Okay, a long lecture, but that's the end of that lecture. Have a good day.